Let's talk about sequences. If we have something that is changing, it could be changing continuously, but if we look at discrete increments of time, we see this sequential picture here. Here's another example. We're just looking at this at discrete increments. Well, that's like a sequence. A sequence is a function whose domain is the set of positive integers. The functional values a sub 1, a sub 2, a sub 3, a sub n, and so forth are the terms of the sequence, and the term a sub n is called the nth term. These are some different notations. We may put them in set brackets, a sub 1, 2, 3, and so forth. We may just put a sub n in set brackets, and this represents the same thing as this. Another way we can do that is put it in and we can say n equals 1 to infinity, so it takes on all positive integers. Here's an example of a sequence, and as we look at this sequence we can see a pattern. In fact, we can see to get to the next term in the sequence you just add 3, add 3. So we could express this sequence as saying a sub 1, the first term is 1, and then the n plus 1 term is the nth term plus 3. So it basically says take any term and add 3 and get to the term after that. This is called a recursive formula or recurrence relation because it basically tells us how to get the next term, and this one is based on the term in front. Now this is great because it's easy to get seeing the pattern add 3, but what if I needed the 100th term? I would need to know the 99th term so that I could add 3 to get the 100th term. We could express this sequence another way. We could look and see we're going to be adding 3 no time for the first term, 1 time for the second term, 2 times for the third term, 3 times for the fourth term, and so forth. And so then we could generate a formula from that, and that would be 1 plus 3 times n minus 1, and if we distribute through and combine like terms, that would be 3n minus 2. This is called an explicit formula because it explicitly states what any given term is. Now on this specific one, if I put in 100, so a sub 100, the 100th term, I could put that in here, 100 times 3, 300 minus 2, and I would know that the 100th term was 298, and I didn't need to know the term in front to do that. So 2 different ways to express formulas for sequences, recursively or explicitly. A basketball is dropped from 20 feet high. Each time the ball bounces, it rebounds to 80% of its previous height. Let h sub n be the high point after the nth bounce. So here we see what this basketball does, and after each bounce it goes only 80% of the height from the original. So our original height was 20 feet, 80% of that is 16 feet, 80% of that is 12.8 feet, and so forth. We could write a formula then. The height for the nth bounce would be the 20 where it started times 0.8 to the n. Then we could find the height of the 9th bounce by taking that 20 times 0.8 to the 9th, which would be 2.7 feet. This is a sequence that lists the height for each of these terms, and we've got a formula so we could find it for any given term. Here's another example of a way to express a sequence, and basically if we let n equal 1, we could get the first term here, which would be negative 1 times 1 plus 1, which is 2, so negative 2 over 3 to the 1. So that would give us a 2/3. And then we could put in a 2, negative 1 squared, so it's going to be positive. 2 plus 1 is 3, and then this would be over 3 squared, so we can see what that would give us. Now we could also express the sequence like this, 2 different notations meaning the same thing, putting it in set brackets or writing a sub n. And we could generate each of those terms by first putting in 1, then putting in 2, and getting the 3/9, so it will reduce, but we'll leave it like that so we can kind of see what we do. Then putting in 3, we would have a negative 1, 3 plus 1 is 4, over 3 to the third, which is 27, and we start to see a pattern that alternates signs. The numerator increases by 1, the denominator increases by power of 3, and so we could see the pattern and continue writing terms in this sequence. We could also plot this sequence to see what it was doing. Here's our negative 2/3, and then our 3/9, then our negative 4/27, then our 5/81, and so forth. And we could see what that sequence was doing. And we see here that it looks like it's getting closer and closer to 0, but alternating on either side. As we look at this sequence, a sub n equal 1 over 2 to the n, if we put in 1, we get 1/2. If we put in 2, we get 1/4. If we put in 3, we get 1/8. We could continue doing this to see what this sequence was doing, and we can see that these terms are getting smaller and closer to 0, remaining positive but getting closer to 0. As we look at this sequence, n over n plus 1, we could go ahead and put in 1. And if we put in 1, we'd get 1 over 2, or 1/2. And then we could put in a 2, and we'd get 2 over 3, 2/3. We could continue doing that, putting in a 3 and a 4 and so forth, and watching to see what this would do. And as we let n become larger and larger, we get closer and closer to 1, because if n is very large, like say n was 1 million, this would be 1 million over 1,000,001, which would be a number slightly less than 1 but very, very close to 1. So we can see if we plotted the terms of this sequence that they would be getting closer and closer and closer to this value of 1. We could then say the limit as n approaches infinity of n over n plus 1 equals 1. So a sequence can have a limit if, as we let n get very large, these terms approach this value. So let's look at a definition of the limit of a sequence. A sequence a sub n has a limit L written, limit as n approaches infinity, a sub n equal L, or a sub n approaches L as n approaches infinity. So two different notations for expressing this idea of the limit of a sequence. If we can make the terms a sub n as close to L as we'd like by taking n sufficiently large. So this is kind of summarizing what we saw. It's not a precise definition. We're going to have that in just a minute. But basically it says it has this limit L. If we get far enough out in the sequence, we can get as close to L as we'd like. If the limit exists, we say the sequence converges, and this is going to be an important word we're going to be hearing a lot of. So if the limit exists, the sequence converges. Otherwise, we say the sequence diverges. So if it is not approaching a limit, it is a divergent sequence.